Before we get back to the modeling of combinational subsystems, we'll briefly look at the notion of glitches. Glitches are unwanted transitions present at the output of combinational circuits which affect their signal integrity. With the help of a simple example, we'll see how glitches occur in a combinational circuit. For illustrating glitches, we'll take the example of a simple two-level circuit and or circuit which implements a sum of products expression. So we have a two-level circuit AB plus say A bar C. So you have the first level which consists of the AND gates and the second level which is the OR gate. Let us label the intermediate outputs as G1 and G2 and the final output as F. Now to begin with, let us assume that the inputs A and B are at logic 1 and C is also at logic 1. So it follows that A bar is at logic 0. Now what about G1 and G2? G1 being the output of the first AND gate is the product of A and B. So G1 also is at logic 1 and G2, which is the ANDing of 1 and 0 because A bar is 0. So G2 is at logic 0 and the final output which is from the OR gate will be understandably at logic 1. So this is the scenario at the beginning. Now let us assume that the input A alone is switching. The input A alone is switching from 1 to 0. The other inputs remaining the same. We are assuming that the input A alone is switching from 1 to 0. Now let us see how this impacts the circuit. There is the input A bar, which is the output of the inverter. So we can expect the output of the inverter to switch to 1 after some delay, which is equal to the delay of the inverter. Now the output G1, which is the AND of A and B, will now switch to 0 following the delay which is equal to the delay of the AND gate. So G1 will switch to 0 from 1 after a delay which is equal to the delay of the AND gate. And you can see here that I have shown this transition occurring at a later instant when compared to the transition A bar. This is because the AND gate typically will have more delay than the inverter. Now the change in A bar has to reflect in the output of the second AND gate, that is G2, and this will be equal to this will occur at an instant which is equal to the delay of the AND gate following the transition at the output of the inverter. So after a delay which is equal to the delay of the AND gate, we can expect the intermediate output G2 to switch. Now this leads to an interesting scenario, because now you have an interval, you have a short interval where both the inputs of the OR gate are at logic 0. There is a short interval of time where both the inputs of the OR gate are at logic 0. So the output of the circuit momentarily switches to logic 0 before returning to logic 1, which is the steady state. So again I'll explain. We started with the combination A equal to 1, B equal to 1 and C equal to 1. The expected output for this was of course 1. Next we considered the combination A equal to 0, B equal to 1 and C equal to 1, which means only the input A is switching with the other inputs remaining the same. Now for this input combination also, the output is a 1. So ideally, even though the input A has switched, we would expect the output F to remain static, to remain unchanged at logic 1. Whereas, due to the delay of the gates, in actual hardware, we are seeing that the output F is momentarily switching to 0 before reverting to 1. This is exactly what we call as a glitch. And this particular glitch is said to be caused by an anomaly in the circuit, which is called a static 1 hazard. Or rather, we can say that this glitch is due to the presence of a static 1 hazard in the circuit. So the key takeaway here is that this is similar to a noise signal, because it's an unwanted transition. It's a spurious transition. But it is not caused by any external source. It is caused due to an imbalance in the delays in the various paths of the circuit. So this imbalance is internally caused, and it gives rise to a noisy behavior, a momentary noisy behavior. And it's quite possible that this will propagate to other gates in the system. Now, how this is handled, we will see later. But for the time being, it is sufficient if you understand that input transitions in a combinational circuit can give rise to glitches which are caused purely due to internal causes. These glitches are not caused by any external noise such as EMI. These glitches are purely caused due to the imbalance in the propagation of the input changes, which eventually gives rise to some temporary logic transitions in the output. So it is important to understand that if we use the outputs of combinational circuits directly for driving an external load, these noise signals caused by the glitches, they are also likely to propagate to the load, which is not a desirable feature. So later on, when we take up sequential circuits, we will see that the outputs of any system have to be registered, which means they have to be routed through a flip-flop. We will see the details of how this is done when we take up sequential circuits. Now I will illustrate how a synthesizable code is translated into an equivalent hardware. It is always important that when we model systems using HDLs, we should have a feel of the underlying hardware. So I have taken a very simple example consisting of single behavioral block, single behavioral always block. So the always block consists of a single if then else statement, which is dependent on a single input called select. So if the select input is 1, then the sum output will be equal to the sum of two inputs A and B. Whereas if it is 0, the sum output will be equal to the difference of the two inputs. So you can see that this is a rudimentary ALU. And from the if then else structure, it is also obvious that a mux will be synthesized from this code. The basic template is that of a mux, and the two inputs of the mux will be from two different arithmetic modules. So that is what we can infer from this small block of code. Now for verifying this, of course, I have written a small test bench. I will share all these codes. I have assigned two different sets of values for A and B for each value of select. When select is 1, A is 4 and B is 3. Whereas when select is 0, A is 12 and B is 14. So these are the two sets of inputs I have assigned for verifying the circuit. Okay, let us see what happens when this circuit is synthesized. I have already synthesized this block of code. I will show you the schematic of the synthesized circuit. So just as we did last time, we will go to the elaborated design, and the outcome is just as we expected. There is a mux corresponding to the if then else block, and the two inputs of the mux are routed from an adder and a subtractor. So this is a simple illustration of how a block of code is synthesized into a hardware netlist. Okay, now let us try to simulate this block of code. Let us first start with behavioral simulation, which just simulates the code for its functionality. So what do we have here? Yes, you can see that the select input is initially set to 1, which means that the output of the mux will be from the adder. So the inputs are 4 and 3, and understandably the output is 7 because the mux will be taking its output from the adder. Now when I make the select input 0, the mux is expected to take its output from the subtractor. So there are two inputs, 12 and 13. 12 and 13. So we are basically subtracting 13 from 12, which will yield a negative number. That is, we would expect the value to be the negative, the 2's complement of 0, 0, 0, 1, which is 1, 1, 1, 1, or F, as shown in the simulation waveform. Now again, when I am when I am switching the select input to 1, the mux output is routed from the adder. That means now the expected output will be the sum of 12 and 13, which is 25. In binary, 25 is 1, 1, 0, 0, 1. Since we have declared only a 4-bit vector for the sum output, only the 4 bits of the output are shown. The most significant bit, which represents the carry, is discarded. So understandably, we can see that the output is shown as 9 or 1001. So this establishes the functional correctness of the circuit. Now let us repeat the same simulation on the synthesized netlist. So let us go to the simulation. Let us select the simulation option corresponding to the post implementation timing simulation. So just as we saw in the case of the simple gate example, when we run the post implementation timing simulation, the delays in the circuit will come into the picture. That means you can expect the outputs to change only after some delay. And one more thing is that when you are simulating a fairly reasonably sized combinational circuit, the effect of the glitches also will start manifesting. So this will be evident when we run this simulation. So let us see what happens when we simulate this particular module after it is synthesized onto an FPGA target. Yes. So let us just zoom in the outputs. Okay. Now when I am changing the select line from 1 to 0, when I am changing the select line, when the select line is 1, the output is 7 in the beginning, and you can see that it is settling to 7 only after a delay, which is the delay of the hardware. Again, when I am changing the select input to 0, the expected output, which is equal to the difference, that is f, is appearing only after a delay. And there is one more phenomenon that you can observe here. That is, the output is not settling down immediately, even after the delay. There are some intermediate transitions. Let me just zoom this part of the waveform where the output is changing. Now, if you observe this part of the waveform, you can see that before the output is settling down to its final value of f, there are a few transitions. There are a few transitions in each of the output lines. So these are nothing but glitches. In fact, there is a dynamic glitch in one of the lines. You have two sets of transitions, and there are static glitches in the lines 2 and 1. It's a static 1 glitch, whereas in the line 3 corresponding to the sum output, the MSB of the sum output, you can see that there is a dynamic glitch. That is, the output first switches to 1, again it switches back to 0, and finally settles down to its final value of 1. So this example that we have synthesized, it serves to illustrate how a code will be parsed by the synthesizer and equivalent modules will be generated. Also, you can see the effect of hazards in the circuit, which eventually give rise to glitches, as we saw in the previous simple example consisting of a two-level circuit. So with this, we will complete this short detour to illustrate delays and glitches. Now, from the next video onwards, we will again move back to discussing more examples of modeling of combinational subsystems. That's all for now. Thank you.